Hello there, Mr. Sutton here with the AB Calculus 616 Extra Practice Solutions on free response area and volume problems. For this no calculator free response, we have the inside of a funnel that's 10 inches tall, has circular cross sections, and they're telling us that at height h, the radius of the funnel is given by this function here, and they're telling us this is in inches. So for the first part of this problem, they want us to find the average value of the radius of the function. So in general, we're going to have 1 over the interval length times the integral of from 0 to 10 of whatever you're trying to average. So in this case, we're going to do 1 over 10 minus 0 times integral from 0 to 10 of this radius function. So I'm just going to write it all in there, 1/20th, 3 plus h squared, and then this is going to be dh, because those are the input variables there. We have to do this one by hand, though. So I'm going to take out this 1 over 20 to start with. So this is going to be, let's see, 1/10 times 1/20th. That's going to be 1/200th. And now let me actually go ahead and take the antiderivative of the stuff left. So this is going to be 3h plus, this bumps up to a 3, so we have 1/3 h cubed. And this is being evaluated from 0 to 10. So I've got the 1/20th outside. I've got, let's see, 3 times 10 plus 1/3, 10 cubed. So all of this stuff with 10 plugged in. And then we're going to subtract all of this stuff with 0 plugged in inside a big parentheses next to that multiplier out there. The stuff with 0 is just going to be 0. So we have the rest of this stuff in here. Now, it's important to note at this point, since you've got all constants, you're actually done with the problem. Just stick units on the end and call it a day. But if we do simplify it, inside here we've got 30 plus, let's see, this is 1,000 over 3. And then if we want to combine all this, we've got, well, let's see now, this is going to be 90 thirds plus 1,000 thirds. So that's 1,090 thirds. Multiply by 1 over 200, that's 1,090 over, that's going to be, let's see, 600. And then if we want, we could just take off a 0 from each side to reduce that. So 109 over 60, and I don't think that goes down anymore. Put inches on the end because that's what they told us the radius units were, and the average units are the same as the regular units. And now we're as done as we can be on this. For this part of the problem, we want to find the volume of the funnel. Now, although this doesn't have any kind of axes attached to it, you could treat this as kind of a solid of revolution problem. And you can think of this as they basically revolved around some vertical line, the way this is written here. So we're going to start, just like with those problems, by finding the area of the cross-section. Since we're going around this line, and there's really like no separation between this axis of revolution and the bounded region that you would be revolving around it, we're going to treat this as a disk kind of problem. And it's going to be a function of height here. The height determines the radius, which determines the area of the cross-section. So I'm going to write a of h equals pi r squared. And then in this case, r they gave us, it's this stuff right here. So it's all of this stuff squared with a pi next to it. Now, since I have to integrate this by hand, I'm actually going to go ahead and simplify this a little bit. So if I square everything in here, I've got 1 over 400, which I'll yank outside here to be with pi, so pi over 400. And then I've got this parentheses now that's being squared. I'm actually going to expand that because I'm going to need to do it anyway for my integral. So this is going to be, let's see, 9 plus 6h squared plus h to the 4th. And now let me integrate this. My volume is going to be the integral of this thing from, let's see, 0 to 10, because we want the volume of the whole funnel here. So we've also got this pi over 400. I'm going to yank outside the integral because I don't need to touch that until I do everything inside here. And now inside we've got all this stuff with a dh. Now to go by hand here, antiderivative time. So we have the 1 over 4, or pi over 400, of course. And we have 9h plus, this bumps up to a 3. We're going to have 2h cubed plus 1/5 h to the 5th. All integrated or evaluated from 0 to 10. So we've got pi over 400, and then we've got all of this stuff with 10 plugged in, minus all of this stuff with 0 plugged in. But I'm kind of short on space here, And I know that when I plug 0 into each of these things, it's all just going to be 0. So I'm just going to say minus 0, just to show people that, hey, I did actually plug in 0, but this is what it gets me. All right, let's do the rest of this. Now, it's actually all constants. So at this point, if you were to put units on the end, and since it's volume here, this would be cubic inches, you would actually be done with the problem. But if we want to simplify it, what do we have in here? This is, let's see, 90 plus 2 times 1,000, so 2,000, plus a fifth of, this would be 100,000, so this would be a 20,000 altogether at the end there. And then adding all of this together, this is going to be, let's see here, 22,090 pi over 400, which I can reduce to, let's see, take a 0 off of all of these. So this is actually going to be 2,209 over 40 with a pi on top. And don't forget the cubic inches. For this last part of the problem, they're saying that this funnel has some liquid that's draining at the bottom. And at the instant when the height of the liquid is 3 inches, somewhere down here, I guess, the radius of the surface is decreasing at 1/5 inches per second. We want to know at this particular instant the rate of change of the height of the liquid with respect to time. So we've got one rate of change. We're asking for another. This is a related rates kind of problem. So we're going to have to take this formula that relates everything here, the radius and the height, and implicitly differentiate with respect to time. Before I do that, I'm going to just distribute this 1/20th, just because I think this is going to work out better if we just have a polynomial versus this kind of factored version. So I'm going to say r equals 3/20 plus 1/20 h squared. And now let me go ahead and take the derivative. So on the left, I've got dr over dt. On the right, 3/20 gets differentiated away. That's a 0 for the derivative. Plus, this is going to be 2 over 20, or 1/10 h. And don't forget the dh over dt, because you just took the derivative of h, which is a function of time. Now let's take stock of what we actually have for information. Eventually, they want us to find the rate of change of height. So we're solving for dh over dt. That means we better have stuff for dr over dt and h. So they said at the instant when the height of the liquid is h equals 3 inches. So they literally said h equals 3. So there's that. And then they said the radius is decreasing at a rate of 1/5 inches per second. So that's saying dr over dt is negative 1/5 because it's decreasing. Let's plug all that in now, because that's all we needed to solve for dh over dt. So we've got negative 1/5 equals 1/10 times 3 times dh over dt. So let's see here. What can I do? If I multiply everything by 10 to get rid of the fractions, that's negative 2 equals 3 dh dt. And then dividing by 3, I've got negative 2/3 for the value of dh over dt. I do need units on this, though. So since this is the rate of change of height, and height is normally measured in inches, this would be inches per second, just like the radius. For this no calculator free response, we have this function defined by 6 over 1 plus x squared, and they gave us a nice little graph of this. R is the shaded region bounded by this graph, and our horizontal line y equals 3. We want to find the area of R for the first part of this problem. So to do this, we're basically going to be integrating from left to right, going top minus bottom for our functions. So that means we're going to need limits of integration and also something to put in the integrand. Let's start with the limits of integration. So our bounded region starts here at what appears to be negative 1 and ends at 1. But just to be on the safe side, let's make sure that's actually the case. So I'm going to set f of x here equal to 3 to find those intersection x values. And just doing a little algebra here, multiply both sides by 1 plus x squared. That's 3 plus 3x squared. Subtract 3, divide by 3. You've got x squared equals 1, so then x equals plus or minus 1, which is exactly what it looks like in the graph, so we just confirm that. So now we're going to have the integral from negative 1 to positive 1. This is going to give us the area here. And inside, we're doing top function minus bottom function. So that's 6 plus x squared, or 6 over 1 plus x squared minus 3 dx. And I'm going to have to integrate this one by hand. It's a no calculator problem. So the good news is my antiderivative for this first term, this is really just going to be 6 arctan, because derivative of arctan would be 1 over 1 plus x squared. So you have 6 arctan minus 3x, and this is again evaluated from negative to positive 1. So plugging in some things here, we've got all of this with 1 plugged in, minus all of this with negative 1 plugged in. And at this point, believe it or not, these are all considered constants. Even this arctan business is considered a constant. So you're actually done with the problem. But if you wanted to risk it and keep going and simplify, you could. So arctan of 1, that's going to be pi over 4. This is the angle at which we have a tangent of 1, a slope of 1 for the angle. So this is 6 times pi over 4, which is going to be, if you reduce that, let's see here, 3 pi over 2 minus 3. And then over here, this becomes arctan of negative 1. That's going to be negative pi over 4. So this would be negative 3 pi over 2. But it's going to become positive with this negative out here. And then we have, let's see, positive 3 inside, but we're negating that. Aren't you glad you decided to simplify, right? There's a lot of places where you can definitely make a plus-minus mistake on this. So we've got 3 pi over 2 plus another 3 pi over 2. That's 6 pi over 2, or 3 pi. And we're subtracting 6 when all is said and done from that. So that's as simplified as this is going to get. For the next part of this problem, they want us to write but not evaluate an integral expression for the volume when r is revolved around the horizontal line y equals 7. So this is where it's kind of nice that this is a no calculator problem, because they don't actually expect you to evaluate this, but you do need to set up the integral. So let me start by drawing this line up here. It's somewhere up here. I just wanted a visual here. Now I see that my bounded region and my axis of revolution, they're not flush, so that means I'm going to have a space in here, so I'm going to need to use washers for my area cross sections. And I'm still integrating left to right here, so this is integrating with respect to x. So I'm going to say a of x equals pi times big R squared minus little r squared. Big R, that's the distance from my axis of revolution to the further away boundary of my bounded region. So that's going to be 7 minus this horizontal line of 3. So I'm squaring that, and I still have this pi kind of hanging out in front of everything. And then the other thing I'm going to be squaring, the little radius, that's going to be axis of revolution minus the closer of the bounded functions. So 7 minus f of x was the name of this thing. And I'm going to square that and subtract that from everything. So that's a of x. All of this is just a of x. Now to get the volume, I just need to integrate this cross-section area from the interval from negative 1 to positive 1. So that'll be my volume, integral from negative 1 to 1 of a of x dx. And they didn't say we had to evaluate it, so we're done. For this problem, they're telling us that h of x is the vertical distance between the point x comma f of x, so basically some point on this f function here, and the horizontal line y equals 3. So we just want to find the rate of change of h with respect to x at x equals 2. So now if you're finding vertical distance, we're talking about absolute value of distance here. And this is a little bit tricky because at some points f is above the horizontal line, at some points it's below. So if you just straight up subtract, then you're going to end up getting negative numbers sometimes. You could stick an absolute value out there, but eventually we're asking for the rate of change of h, so that's going to be kind of annoying to take a derivative with an absolute value thrown in as well. But now look at what they're doing. They're doing this at x equals 2 over here. So after you get to 1, you just have to subtract in an order that gives you a positive number. So I'm going to say that for x greater than 1, at that point the horizontal line is higher than the function, so you need to do 3 minus all of this stuff to get the vertical distance. So I'll write h of x equals 3 minus this, and I'll put this as a negative exponent rather than writing it out in fraction form. That'll just help me take the derivative in just one moment. All right, time to actually take the derivative of h now. So this 3 gets differentiated away. Using our power rule, negative 1 and negative 6, that's going to be positive 6 times 1 plus x squared to the negative 2 times the tail of 2x. We have an inner function of 1 plus x squared, whose derivative is 2x, so don't forget your chain rule here. And I'm about to plug something in. They want us to find the derivative at x equals 2. So just to clean things up a little bit, I'm going to write this as 12x over 1 plus x squared quantity squared. So all I have to do at this point is plug 2 into this thing. And I could just stop here and be done, because this is all constants. But if we do choose to simplify, we've got a 24 up top. Down here, this is 1 plus 4, so 5 squared is 25, 24 25ths. For this calculator-based free response, we have these two functions, f and g, which we should probably put in our calculator soon, and r and s are the two regions enclosed by these functions. So for the first task, they want us to find the sum of the areas of r and s. So one way you could do this is you could think of each of these as a top minus bottom from left to right sort of integral situation. And you could figure out this intersection point here, which eventually we'll call P. And you're going to have to do top minus bottom from 0 to P for one integral. But then you're going to have to switch the order you're subtracting for the other integral from P until 2. That's one way to do this. But since you're allowed to use a calculator, you can actually account for this function change halfway through, or whatever this p-value is way through, by using absolute value. So the way I'm going to do this, I'm going to integrate from 0 to 2. I'm going to take the whole area there, the whole integral, the whole interval, and I'm going to say absolute value of, well, if I'm doing absolute value, it doesn't really matter what order I subtract in, so I'm going to do f of x minus g of x. I don't really know which one is the top function where at this point, but I don't really need to know, because I'm just using absolute value to force all those subtractions to come out positive no matter what. And don't forget the dx. So now let me just plug this in the calculator. So I've plugged f of x into my y1, and g of x is y2, and I'm glad I never have to write those out on the calculator again. Those are some pretty involved functions. So to plug in my integral here, I've got integral from 0 to 2, and I did alpha window and pulled up absolute value, and then alpha trace for y1 and y2. Subtracting those with a dx on the end, we get about, let's see here, takes a while to do this because of your absolute value, but eventually your calculator comes back with a value of 2.004. For this part of the problem, they're telling us region S is the base of a solid whose cross-sections perpendicular to the x-axis are squares. We want the volume. So in order to do this problem, we're going to need a few things. First off, we need the limits of integration for region S. So we kind of got away with not figuring out this intersection point on part A, but now we can't put it off any longer, so we're going to do it. Let's figure out where f of x and g of x equal each other. So again, I've got these entered as my y1 and y2 respectively on the calculator. I'm going to graph these now, and then I'll find the intersection. Now for the window, I'm thinking 0 to 2 is going to give me a good picture. I mean, that's what they have in the graph that they gave us. So let me do a zoom 0 off of that window. Zoom fit. And here's what my calculator is showing me. So it looks like f of x is the bottom function initially, and then g of x is this initially top function. F of x just is kind of like a little piece of a parabola. I mean, it is exponential, but with some other bells and whistles. And then g of x is just all polynomial. It's giving us this wavy action across this interval. So intersection, let's do second, trace, and then intersect. And my spider's already about where it needs to be, so let me just press enter 1, 2, 3 times to get about 1.0328, and I'll call that P on paper here. So now I can just use P on paper instead of writing all this out. And on my calculator, I'm immediately going to quit out of my graph, and I'm going to store the value I just got as alpha P. Again, I want to be able to use this again without typing in a whole bunch of stuff. So those are my limits of integration. If I'm doing a region S, I'm going from P to 2. We need to get the area of the cross sections though. Now they said these were squares and it was perpendicular to the x-axis. So this is going to be a function of x then if I've got these of essentially vertical bases of these squares. So I can write a of x equals s squared, and the side of the square is just the distance between these functions. So we have to be kind of cognizant of which one's on top. I mean, technically, you're going to be squaring it, so it doesn't really matter if you subtract them in the wrong order, but just for the sake of accuracy, this is f right here, and below we've got g. So this is going to be f of x minus g of x that I'm squaring over here. Now I'm going to go ahead and set up my integral. So my volume, that's going to be the integral from p to 2 of this a of x that I just wrote with a little dx after it. Time for the calculator again. To make this a little less ungainly on my calculator, I'm going to do y3 for my area function. This is just f of x minus g of x, y1 minus y2, all that squared. Quitting out of there now, let me do math 9. Integral from, let's see here, we said p to 2. Okay, so that's going to be alpha p, and then 2 for my upper limit of integration. And then I'll do alpha trace y3 for the integrand, because that's where I stored my area function, and then dx. All comes out to about 1.283. For this part of the problem, they're telling us h is the vertical distance between f and g in the s region here. They just want the rate at which h is changing with respect to x when x is 1.8. So basically, let's write out the h function and then just take the derivative of that thing at 1.8. H is just going to be f of x minus g of x, just top minus bottom function here. And then to take the derivative and plug in 1.8, well, the nice thing here is when I take the derivative of all this, I don't have to even write it out algebraically because I'm just taking the derivative at a specific spot. So I'm just going to write h prime of 1.8 equals f prime of 1.8 minus g prime of 1.8. Since I'm just taking the derivative of these functions at a specific spot, I don't need to tell you what f prime of x and g prime of x actually look like algebraically. So let me do this on the calculator now. So I'm going to be a little bit clever about how I do this on the calculator. I'm actually going to put basically f minus g in y4, and then I'm just going to take the derivative of y4 at the x value 1.8. So this is one way of doing it. Let me just show you that. So math 8 derivative dx, and now I put f minus g in alpha trace y4, derivative at 1.8, enter. Gives us about negative 3.812. Now another way of doing this, you could have done all of this stuff for y1 and then subtracted all of this stuff for y2. This just streamlines it a little bit so you only have to do math 8 once. So then that answer is what we're looking for.